I'll quickly run down our agenda today, starting with the intro, that's right now. Then we're going to dive into the lightning talks. Each developer is going to present for about 5 minutes on their project. And then finally, we're going to do some Q&A. And we invite all of you to ask any questions you might have about the work presented in the lightning talks or about OMOP ETL in general. I even invite the panelists to ask each other questions. I think it's pretty rare that we have that much OMOP ETL expertise in one meeting all together across lots of different institutions. So I think we should really take advantage of this opportunity to share knowledge. And just one note, please save your questions for the end. And then once we finish the lightning talks, use the raise hand feature if you want to ask something. And then, yeah, finally, we'll just do a little break at the end to give folks some time to chill out before the next session. And here's our panelists. Everyone's going to introduce themselves before they speak, so I'll save you the repeats, and I'm going to turn it right over to Vishnu to kick us off.
Thank you, Katie. Can you see my screen?
Yes, we can see your screen and we can hear you. Thanks.
Right. I'm going to blitz through this, saying that we said it was a lightning talk. Thank you very much for inviting me to this. I'm honored. I'm just looking at Paul's presentation of the number of people that are part of this community and how much they have contributed. I'm well and truly a very, very early developer, if you like, within the community. Let's see. Right. So I am a consultant surgeon at Lancashire Teaching Hospitals. We are located in the northwest of England. That's part of my role. That's about 30% of my role. The remainder 70% I work for digital. I lead the Lancashire and South Cumbria Secure Data Environment Program. Anyone from the UK will know that we have a large nationwide program for building trusted research environments. I also hold an honorary chair at Lancaster University. So we are a major teaching hospital and a regional trauma center. We have 2 sites. And today I'm going to speak about about our data landscape. I don't think it's particularly different from a lot of other big hospitals. How we went about transforming into OMOP, and very briefly touch upon the analytics infrastructure that we've got deployed alongside that. So this will be familiar for most people here. A patient journey through a hospital is very complex. When a patient comes in, some of their data goes into an EPR. They go have a colonoscopy. The data sits in a different clinical application. The back endoscopy, radiology sits in a different system. Cancer data sits in and they're all. Our EPR sits. Data goes into an Oracle warehouse. A lot of our cancer data goes into SQL Server. Our laboratory data goes into Sybase, which actually is in German. So one of my engineers has learned German to write the SQL queries to map data in. And when you take that outside of the hospital, the number of places that we store data about our population simply explodes. It's unmanageable. So I went on we have access to the OpenAI endpoint, and I said, hey, depict the OMOP common data model as a person-centric data model. And it came up with these 2 nice graphics. And this ties in nicely. I think the one on the right ties in nicely with the Odyssey community. It's the superpower of the community, bringing in all the data silos together into one big. So I quite like that. So we started, as most ETL programs for OMOP work, we started looking at White Rabbit first. Our Oracle warehouse has got 1,000 objects in it, undocumented. White Rabbit failed to run successfully on it. We tried to select it. We spent 2 weeks with White Rabbit, but we didn't know how to make it work. We looked at Rabbit in a hat, and then we settled on. We looked at Rabbit in a hat, and then I said, hey, this is what our data lineage looks like. Part of our data lineage looks like on DBT for our ETL. So you can see how complex it is. And this is about 80% of our data for one hospital. So this shows, each node there is a table or a view. And from the left to the right, it takes our source data and puts it into OMOP. So you can see that it's challenging doing some of this work. So we picked a tool called DBT. It's an open source tool. I'll drop some links in the chat after my presentation. It's called Data Build Tool. There's an open source version. There's a hosted cloud version as well. We chose to use the open source version. And what it allows you to do is build your entire ETL as SQL with very minimal Ginger templating on top of it. So anybody who comes from a Django or Python background will know Ginger. The learning curve is very, very shallow. I'm not sure if my data engineers are here today. They spent 2 weeks learning it. So they had really good SQL experience. 2 weeks later, they were writing DBT code. It's allowed us to work as a team. It gives us data lineage built into it, documentation, it's self-documenting. And if I think I'm about 2 minutes into my presentation. I may even squeeze in a live demo if I can. So we built multiple layers. I'm sure everybody's got a different way of doing it. So we have a multi-layered modeling approach to our ETL, and the layers are based on what functions happen at each, what operations happen at each layer. So we have a source layer, we have a vocabulary layer, we have a staging layer, and finally we have an OMOP layer. And I'll drop the entire DBT lineage is published online. So you can go and browse everything that we've done, every line of code that we've written, and all of the lineage. So I'll drop that in the chat as well in a minute. So you can have a look at it. So we'll start with the vocabulary. We used Usagi. Usagi has been fantastic for us. We used Usagi. So the Usagi outputs get saved as CSV files, and DBT has this concept of seeds. Essentially, you save the CSV files into Git, and DBT will automatically convert those into tables in your warehouse. So that's what. So we have various domains. We use Usagi. The outputs became seeds. Seeds get incorporated into the ETL lineage. Here's a little example of one particular OMOP table or person table and the number of different sources that go through the transformative process, going from source into staging into vocabulary to finally make your person table. That's possibly one of the simplest lineages there. When you start looking at things like measurement or observation period or drug error, it gets really complex fast. What DBT allowed us to do is use OMOP for more than research. So we've been able to reduce our refresh time of OMOP. I think we started off on a monthly. Now our OMOP instance refreshes every morning. So 9 o'clock every morning, our OMOP data is as current as of midnight the previous night. And this is a little a snippet of the lineage that shows how we've gone about doing our incremental refresh. So only the new rows are transformed into. This is not for all the models. This is just for some of the biggest tables. Some very brief summary stats. We've got about 1.8 million patients, 400 plus measurements. These obviously increased by about 1 million a day, I think, at the moment, or 500,000 a day. We bring in multiple data sources. Like I said, it refreshes every morning. We're using it for direct care intelligence as well as research. What are we doing next? So that bit that I've just shown you is our bronze layer. So we're now building something called the OMOP medallion architecture. This is where maybe we can work with the community, because once you've got data mapped into OMOP as bronze, then the silver and gold layers, whatever we build, will be useful for the rest of the community if you're using DBT. And if you're doing something, that will be useful to us, because some of the operations you have to do to get your OMOP layer through the data quality checks to make it network conformant are the same. Have we got 1 more minute? Okay, did they? Lost. Perfect. We put a poster in the OHDSI Global Symposium, and we couldn't travel to the States, unfortunately, last year, but I made sure, thank you very much for the OHDSI community for putting our poster up. And there we are. I've got a little arrow pointing to our poster there. My data engineer is really, really shy. That's the top of her head there. I'm not sure if she's here today. Quinta Ashcroft, she's done about 80%, 90% of the work on this. So that's the ETL side of things. So, I did say the title of my presentation was the hard way is the easy way. Yes, there was a steep learning curve with DBT and the way we went about doing things. But now that we've done it the hard way, bringing in additional data sources is trivial. And we're now going out to map another hospital's data into OMOP. And our strategy is that we'll have one OMOP instance between the two sites. And there are 5 hospitals in the region, and our vision is that in a few years' time, we'll have a single OMOP instance for the entire region. That's the data. The OHDSI stack is deployed on Kubernetes at the moment. And the OHDSI stack forms part. I think, Paul, you spoke at the data science meeting at Lancashire Teaching Hospitals maybe 3 years ago now, when I presented our Jupyter Hub instance on Kubernetes, and you said your precision medicine platform, I believe, runs on Kubernetes as well. So our Odyssey stack is now running on Kubernetes. We are engaged with the Databricks working group because our OMOP data sits in Databricks. There are some issues with compatibility, but we'll work with the community through that. So this is not, we say DevCon. This is not about the software. This is not about the tools. This is very much about the people. So for me, all of this has allowed me to kind of build up the skills within the region around a modern stack. My 2 data engineers are doing PhDs, but they're both. One of them is focused, the entire PhD is focused around the data engineering. But we've been able to secure multiple grants. We are a founding member of the UK Odyssey chapter. We're looking forward to engaging more with the community and learning with you guys. I think I may have run out of time, and I may keep the demo for a different day, Katie.
Yeah, and maybe during Q&A, someone wants to ask for a demo.
Perfect. Thank you very much for the opportunity, though.
Thanks so much. All right, next up, we've got Roger.
So thanks for having me, Katie and Paul. My name is Roger Carlson. I work at Corewell Health as a senior data analytics engineer. Corewell Health is a large healthcare system servicing central and lower, basically all of central and southern lower Michigan. So what I'm going to talk about today is moving OMOP to the cloud with DBT and Snowflake. I really appreciate Vishnu's presentation because it simplifies mine a great deal. So just remember all the things he said about DBT. And we presented a board here at the 2022 symposium. So our OMOP instance was special purpose built for a network study called the All of Us Research Program, which was funded by the National Institutes of Health here in the U.S. And for it, we enrolled about 12,000 patients. Our legacy system, since we are a Microsoft shop, our legacy, and I should say our source is Epic. So we were sourcing it from Epic Clarity. And since that was in SQL Server, we built our OMOP instance in using SQL Server and SSIS SQL Server Integration Services as the orchestrator. But we really had a hodgepodge of tools. I mean, we were using Management Studio, SSIS, Visual Studio, RedCap, some Oracle, RStudio, Tortoise SVN, and even some custom-built Microsoft Access applications. These were all desktop applications, but somewhere in the around 2020, late in the year in 2020, our organization decided that we were going to move into a cloud computing era using Snowflake. And so we looked at a bunch of different ways to orchestrate Snowflake and came up with DBT for the reasons that Vishnu talked about. Also, Snowflake recommends DBT, so they're very tightly tied together. They're not owned by each other or whatever, but they are. That's what they recommended. So Snowflake is a cloud-based database platform. In our case, it's running on AWS, but it can run on Google or Azure. And DBT is a data orchestrator. It's built around Python. You don't need to know how to use Python. You really only need to know how to use SQL. And so, rather than this hodgepodge of tools we had before, now we're using mostly open source tools like Snowflake DBT. We're using GitHub, still using RedCap, VS Code, DBeaver, and RStudio. So it's a much simpler data set, and it's all open sourced. So our timeline for converting was roughly 13 months total from inception to actually running production for the All of Us. We had 2 people working on it, myself and a colleague of mine, and roughly 21 person months involved in that time. And we did this in 4 phases. Phase 1, we moved our database from SQL Server to Snowflake. And that took roughly 8 months because we were just learning Snowflake. We were just integrating Snowflake, trying to, figure things out as well. So basically from April to December of 21. We also upgraded our OMOP version from 5.2 to 5.3.1, which was the version that all of us was using. So, excuse me. So that was phase 1. Phase 2, then we converted our SSIS process to work against the Snowflake database, and that took about 3 months. From September to December of 21, and it overlapped phase 1 too. So we were able to work in both of them at the same time. And then phase 3 took another 4 to 5 months, and we converted our SSIS process to DBT. And so that, from by July 7th of 2022, we were able to do our full production run and send the data to all of us. Phase 4, if you look in our workflow comparisons on the screen for SSIS and DBT, the ones under SSIS that are marked red were manual processes that we had to do because we weren't able to automate them in in SSIS. We were able to automate most of those processes in DBT, including pulling the vocabularies, pulling our OMOP patient list from REDCap, loading, processing the data, and then loading the CSVs up to the All of Us Google bucket. Early on, we were pulling data out of Snowflake down to our local system and CSVs, and then uploading them to the Google bucket for All of Us, which didn't make any sense because it was in the cloud to begin with, and so it's relatively simple to transfer from one cloud bucket to another, and so that works really, really well. In terms of runtime, you can see that using our legacy system took about 1 hour and 50 minutes, only doing those things marked in green. And when we switched over to DBT using Snowflake, it went down to 5 minutes. Now this is for the 12,000 patients that we had in the All of Us program. So that was a huge decrease in processing time. And then in addition to that, we added our phase 4 in there, that automatic stuff, and that raised the processing time from about 5 minutes to roughly 9 minutes. So still a huge decrease in efficiency, not a decrease in efficiency, an increase in efficiency. And so we are now, our next phase is to build this to work against our entire patient population. And I wanted to have at least a test run of that to give you some idea of how that works. But we're not quite ready for that yet. We have been able to run 100,000 patients, and our base process, without the uploading and everything, went from 5 minutes to about 20 minutes. So a 4-fold increase in time for an order of magnitude more patients. And so that bodes really well, I think, for running the 1 million to 5 million patients that we're going to be running ultimately. So that's really all I have. If you have any questions, you want to contact me at Corewell Health, we're always glad to talk to you. And if Katy posts some of these, slides, I've got some links to more specifics about those products. So that's all for me, and I'll send you back to Katy. Thanks.
Thanks so much, Roger. And yeah, all the slides and the recordings will be posted on OHDSI website after the event. And I'm going to turn it over to Georgie, who, by the way, is calling in from Australia very late at night. So thank you so much for making the time.
Hi, yeah, it's 20 to midnight here. So yeah, that's just to explain if I'm a little bit woolly in the question session later, that will be why. But yeah, thanks for having me. I don't often join these calls because they are at very inconvenient times. So it's nice to have an excuse to tonight. So I work for SPHERE, or Maradulu Budiari Gumal, which is a multidisciplinary research network that spans across southern Sydney. And I sit specifically within the Ingham Institute for Applied Medical Research. And the applied bit in this context just means that all the work we're doing there really addresses practical challenges specifically encountered in the clinic. This just means that everything has a really translational focus, and we're looking for practical solutions for improving healthcare delivery and outcomes. These are the broader themes under which our program of cancer research is structured. All of the domains do have some kind of data element involved, but the observational data space is definitely concentrated under my area of focus, which is reducing variation in clinical practice. And in an effort to facilitate this day-to-day, I spend about half my time working on delivery of an OMOP-centric cancer data platform called SAVAR, which is a contraction of cancer variation. And these are our current stats, if you're interested. And you know, that little box represents so many different pieces of work in reality, but I'm just going to describe one current area of focus just to set the scene for what I want to demonstrate. So Merin in the middle here is an oncology specialist dietitian. And she's leading the co-design of dietetic-specific business intelligence visualizations for the detection, highlighting and prioritizing of variations in practice, specifically in the domain of head and neck cancer. And I call this piece out specifically because I think it's an example of a really great low-cost, high-value supportive care intervention that delivers a proven improvement in outcomes for a really specific but very small population with those complex dietetic needs. And I really wasn't sure how much background I needed to provide for this part of my talk, but just in case you aren't familiar with ORMs or object relational mapping, there's a fair amount of richness and complexity underlying all that. So I'm just going to take a minute to sort of whip through a little bit of the conceptual grounding. Starting with the actual database, I think it's pretty fair to assume everyone has a good mental model for that part. But then there's the application layer, which is where we describe in code a representation of the underlying data model, which allows us to interact with the database records directly as instantiated Python objects. And so what does that actually look like? If we look at the mapping of the concept table for a second, don't worry about the details. Hopefully it's not that hard to kind of draw a straight line between what you know of the OMOP model definition and what's rendered here. But for our purposes, it's just enough to remember that the table definitions are expressed as classes, and you get columns as properties of that class. And the column mappings define the details of the things that underpin that, like the keys and the data types. And finally, the abstraction, which is kind of the guts of the ORM itself, which provides a translation mechanism between the back and front ends of the stack. And it does things like converting Python code into dialect-specific SQL, or instantiating Python objects that represent the results of the executed queries. So great. Why? Well, for one thing, Python objects are way more expressive than the database rows themselves, right? So analysts, we always need to make decisions over and over again when we're applying conventions in the ETL, I think, as well as the final analyses. And we often find ourselves taken by surprise down the line as a factor of ways that we have interpreted these for implementation sort of at the starting part of this process. And in practice, a richly expressed relational algebra can turn many of these decisions kind of into a set and forget sort of situation, with the side benefit, I think, of making the ETL itself inherently validatable at design time instead of just post hoc on the transformed data. So for instance, a concept object that's returned via a unit concept ID has enough context to know that it needs to behave differently to one that was returned via value as concept ID, if that makes sense. This can even extend to the concept object having different behavior depending on further relational details, such as dates or age variables. And finally, here's a couple of specific use cases why you might want to actually apply this. The first here is what I just mentioned, so bringing these data validation checks further up the ETL pipeline. A trivial example, obviously, but we use the validates decorator to intercept an event when an object is created or modified in sort of user code. And in this example, you raise an exception, so it's impossible to actually write improperly formed records to the database, or you choose to intercept and handle and modify the incorrect data before even writing it out. And if you need to reference vocabulary tables or perform domain checks, things like that, you can employ like a class level method, which pulls in additional context when instantiating the class. And it means that you do marginally slow down the application setup, but overall it still performs really, really well because the classes are only imported one time, whereas the validators fire every time you create the object. So the trade-off's pretty easy to make there. And here's a few more examples showing how it's possible to provide a validation for one field relative to another within a table. and also how you can customize the actual event that the validation scripts listen for, which is useful when you want to validate complex objects, such as the episode objects, which are built stepwise. So another use case that we use this for, this is a really simplified version of our visualization stack. And there's a couple of reasons why I like to do it this way, but the main reason is that it's very loosely coupled into layers, right? So it means you can build and reuse the core application logic in multiple places just by changing the way that we interact with the publish API. Here's just an example of that API and how it gets rendered. I just always like to include, just in case anyone thinks I'm showing real patient data. But here's an example of where the same underlying condition logic gets applied as either a normal condition by the condition schema, or you can render it as a cancer-specific schema by applying different serialization logic, starts to pull in the modifier objects as well and nests these below the parent JSON. And this one is one of my proudest problems I've solved through the ORM approach, which is handling of polymorphic relationships between the measurements, observations, and episode events, each of which can point to a number of different target tables. And so having an intermediary class like this, it abstracts away that complexity so it's hidden to the end user. This means that you can conveniently grab all episode events as a collection, and you get that directly via the events property, instead of needing to handle and flatten each joins against each individual target. And the logical conclusion of this is this query, where you can return an individual, all of their nested events, and all of the episode events assigned to those episodes within a single call. And the final one here, these are just a few examples of how we've implemented extended properties to build in a convention logic within the data model definition itself. So it takes care of all of the logic of handling modality of treatment of episodes here. So again, it ends up being impossible to misinterpret conventions. So if you have an agreed implementation of the most important ones, and I've really spent the least time on this one, but I think it has a ton of potential, although we have to really carefully balance the considerations of and performance implications. And finally, I've put this out as a beta version of the libraries. If you want to have a play, feel free, and please let me know what you think. Just do keep in mind it's definitely the beta version, and so it's not a stable code base. So things may shift underneath at this point, but I hope that somebody finds that useful. And I think I may have lost connection in the middle there, but hopefully you got the gist of it.
No, we had you all the way through. Thank you so much.
Oh, great.
And
my VPN started to reconnect, that's all.
Okay, no, all good. So we'll turn it over now to Sam.
Right, good morning / afternoon, everybody. Thank you for inviting me to join what's an excellent panel. Really excited by everything I've seen today so far. My name's Sam Cox, and I'm talking today from my position as technical lead for the Carrot tools. Now, just a little bit about me, just to begin with. After a mathematics undergrad, I did a PhD in maths and geology, looking at modelling the flow of the mantle. That really piqued my interest for high performance computing, and from there I became a research software engineer, which I remain to this day. Nowadays I am in Nottingham, the UK, and I've moved into this, rather than geology and HPC, I now do much more in the field of health data and trusted research environments, things like that. And I'm also currently on 50% secondment to Health Data Research UK, an organisation here in the UK. Today I'm going to be speaking about the Carrot tools, which were largely developed by a big team at Nottingham, Dundee, Edinburgh, and a couple of other places, and continue to be developed to this day. And yes, the Carrot naming is a gentle sort of hat tip to the OHDSI Rabbit naming convention. So what are the Carrot tools, and why did we build them? So gaining access to healthcare data, certainly in the UK and many other places for research purposes, can take a very long time. You can be looking at 6 months or more to get access and all the various governance approvals in place. When you're trying to convert many data sets from disparate places to OMOP kind of at scale, this is an enormous barrier, particularly if you don't have OMOP experts within each organisation who already has access to that data. The Carrot tools are architected in two parts. We have an internet accessible web app here, and a Python ETL tool as a second part. Together, they allow external OMOP experts to design OMOP transformations for datasets using only metadata, not the row level data. And then the ETL process can be run by anybody with a simple command line. So this means because we don't give access to outside OMOP experts to the row level data, then the governance approvals that the architecture requires are much lower, and that's hopefully faster to acquire. So that helps the whole life cycle to move a lot faster from having data to having OMOP-fied data. Now, this wasn't possible previously, so that's why we ended up building the Carrot tools. Now, the original use case was in the area of federated data discovery, where data sets can be remotely queried to provide safe, non-disclosive information about their contents. Particularly, this is in the research sphere, and so we want to enable researchers to decide whether to pursue a lengthy full access data access request, having the knowledge that hopefully the data is what they wanted. Converting to OMOP is a vital step in that process, but data discovery works best also when the OMOP mappings that are being used are somewhat kind of limited, sort of using a standard subset of the full breadth of the vocabulary. So we built Carrot not only with that split architecture, but it also is built to share and to reuse mappings between data sets, what it's previously seen, and also to provide feedback looking across multiple data sets to see whether they could perhaps align on a smaller subset of possible OMOP concepts. It was important that we automate as much of this as possible, so mappings are not only reused when the system has already seen something similar, but also recognize vocabs are automatically mapped to their respective concepts. Oh, have I just lost my screen sharing?
Yes, you have.
Yeah. Let me restart sharing. Right, double checking that's okay.
Yep, you're back.
Yeah. Okay, good. And finally, our ETL tool down here that actually runs and does the transformations requires no SQL from the user, but instead it leverages its internal ORM to build and apply rules. Of course, that does bring some limitations. We can't build arbitrarily complex transformations without the power of SQL, but typically, certainly in our use cases, this limitation is typically outweighed by the convenience of avoiding the use of SQL by the user. So what does this look like in practice? A very short demo here. So here we have a data set, and it's got a table of symptoms. Here we click on the headaches one here. This has been uploaded into our system, and you can see that headache has been automatically mapped by the system because it's already seen that previously. However, the dizzy entry here, it hasn't seen that before, so we can just enter that ourselves. We pop in the OMOP code. Click add, we see that that's identified the code, and then we can go and check that that has now generated some rules that we'll be able to apply to the data later, and then we can download our rules as a JSON file. Okay, so that's essentially in a nutshell our very first tool, everything that does. That mapping rules file can be sent to sit next to the original data set, and we could then run the transformations there. Just to sort of highlight how important it is to automate things, this is a single field in a single table in a single data set, and here the system's automatically mapped 2,500 ICD codes to OMOP. So that's just leveraging the existing power of the Athena database. And then finally, with a single line in a bash command, we can run the transformation. So we tell it what rules to apply to what data and where to put the output. And 5 seconds later, we have 30,000 transformations have taken place. Many of us are developers here, so this is what our stack looks like. We've got our two tools, Carrot Mapper, the web app. It runs in Azure. It's got containerized Django backend and Next.js frontend with a Postgres database behind it, and then the ETL tool that has to run inside the data owner's environment. That's a simple pip installable Python package, but with pandas as well. this is just a kind of sample of some of the data sets on the left-hand side. This is typically UK focused, but some of these things like Public Health Scotland, Generation Scotland are very, very large data research data sets. On the right-hand side, some of the projects and institutions that are using it. So the CoConnect project, which sort of was one of the main drivers for the development of the Carrot tools, that has made more than 10 million patients worth of research records available through data discovery. We're also integrating with things like the East Midlands SDE as well. And finally, I just want to say thank you to a huge number of people. Don't really have time to thank them all. Developers, designers, and our brave beta users, project leads, and some of the organisations that have helped to fund this. And we are continuing to develop. Thank you very much for listening.
Thank you so much, Sam. And last but not least, we have Peter to talk about Rabbit in a Blender.